Okay, so time for us to finish up chapter 9. Okay, so now we'll start to talk about transforming with an exponential model, and then we'll kind of put it all together and see the point of this, but I'll focus more on putting it together in class. So sometimes the relationship between y and x is based on repeated multiplication by a constant factor. That is, each time x increases by 1 unit, the value of y is multiplied by b. An exponential model of the form y equals a times b to the x describes the multiplicative growth. Okay, so a lot of the times money can display exponential growth. If you're talking about interest, it's compounded each time period. Okay, so this kind of just demonstrates that. So suppose you invest $100 in a savings account that pays 6% interest compounded annually. After a year, you will have earned 100 times 0.06, so $6 in interest. Your new account balance is the initial deposit plus interest earned, so 100 plus the 100 times the 0.06, or $106. You can rewrite this as 100 times 1 plus 0.06, or simply 100 times 1.06. That is 6% annual interest, means that any amount on deposit for the entire year is multiplied by 0.106. If you leave the money invested for a second year, your new balance will be 100 times 1.06 times 1.06. So in other words, 100 times 1.06 squared. So that's going to give you $112.36. Notice that you will earn $6.36 in interest during the second year. That's another $6 in interest from your initial $100 deposit, plus the interest on your $6 interest that you earned in that first year. After X years, your account balance Y is given by the exponential model. Y equals 100 times the 1.06 to the X power. Okay, so the table below shows the balance in your savings account at the end of each of the first 6 years. The figure shows the growth in your investment over 100 years. It is characteristic of exponential growth that the increase appears slow for a long period and then seems to kind of explode. It's kind of the difference, if you think about it, between a linear kind of goes up gradually, where an exponential growth kind of goes gradually, and then all of a sudden it's like that rapid or drastic increase or decrease, depending on what it is. Okay, so let's talk more about these transformations. Okay, so if an exponential model of the form y equals a times b to the x describes the relationship between x and y, we can use logarithms, kind of like what we did with power models, to transform the data to produce a linear relationship. So again, this is going to be like the power model, so you're not going to know what power model it is, so we use logarithms. Much like exponential, you're not going to know what the exponential relationship is, so you're going to use logarithms to help you there. Okay, so the following kind of walks you through how to change it to follow logarithm. So you're going to take the logarithm of both sides. Using that property, you'll end up with log y equals log a plus x times log b. Okay, so now we'll kind of walk through, that, but in an example. So Gordon Moore, one of the founders of Intel Corporation, predicted in 1965 that the number of transistors on an integrated circuit chip would double every 18 months. This is Moore's law, one way to measure the revolution in computing. Here are data on dates and number of transistors for Intel microprocessors. You can clearly see it's a curved relationship in here. So kind of like that exponential, right? Gradual, 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 and then that drastic change. A scatter plot of the natural logarithm, so a log with base e or ln, of the number of transistors on a computer chip versus years since 1970 is shown. Based on this graph, explain why it would be reasonable to use an exponential model to describe the relationship between number of transistors and years in 1970. If an exponential model describes the relationship between the two variables x and y, then we expect the scatter plot of x versus the natural logarithm of y to be roughly linear. The scatter plot of the natural log of transistors versus the years since 1970 does have a fairly linear pattern, especially through the year 2000, so an exponential model does seem reasonable here. Minitab output from a linear regression analysis on the transform data is shown below. Give the equation of the least squares regression line. Be sure to define any variables you use. Okay, so just like it's always been, y is representing the y hat is being represented on the graph. You can see it written here. Remember, you're not actually figuring these things out. That will be told to you. You just need to know how to change your regression equation. So instead of putting y hat, we have to put ln of the transistors, which is on your y-axis, okay? This is your y-intercept found in your output, plus here's your slope also found in your output, times, and then because it's an exponential, you're just following what this tells you, which is that it's not changing, it's not transforming x at all. It doesn't in an exponential. Both are changed in a power model. Only your y is changed in your exponential model. So here you're just going to stick with x being the year since 1970. You don't have to transform that. Now I can use my model to predict the number of transistors on an Intel computer in 2020. So I'm going to use that equation that I just found, okay? So the natural log of the transistors, okay, is the y-intercept plus whatever we wrote on the last time. The slope times the 50, okay? So 50 years since 1970, okay? You're not done here. That's not your answer, okay? That also doesn't make sense if you think about it. So now you have to kind of undo the logarithm to find your predicted transistors, okay? So a natural logarithm has a base of e. So the way that we undo this logarithm is by taking a base of e and raising it to that answer that we found, the 25.3562. So we're going to say about 1.028 times 10 to the 11th transistors. A residual plot for the linear regression in Part B is shown below. Discuss what this graph tells you about the appropriateness of the model. Okay. The residual plot, it does show a pattern here, okay? So you could kind of, like I always say, you could kind of trace it around here, okay? So yeah, positive to negative, okay? But the residuals are fairly small in size relative to the transformed y values. Also, the scatter plot of the transformed data is much more linear than the original scatter plot. So I think we can feel reasonably comfortable that we can use that model to make predictions on the number of transistors. Also, let's check what that r-squared value was. Our r-squared value is pretty strong as well. So I think we can say that a linear model is appropriate and that regression line was a fairly reasonable model. Okay, so that's it for videos. The next things that you see in your packet, we're going to discuss them in class. That's kind of where we're going to start to put it all together and make sense out of what it is that we're expected to know how to do in Chapter 9. So that's it with the videos, and we'll tie up here. Also, we have some calculator skills to know in class.